By analogy with the ratio of the arc distance along a curve to the projection of that arc distance along an x-axis, we can talk about the projection of a surface region onto the plane below it. The ratio of the arc distance, the distance along this line to the delta x, is simply square root of 1 plus m squared, where m is the slope, which can be expressed as a square root of 1 plus f prime of x naught squared delta x when we're talking about a segment of the curve near the point x naught f of x naught. In the plane, a delta x is accompanied by a delta y equal to f prime of x delta x, implying a vector normal to the curve in the xy direction, a direct vector to perpendicular, which has the negative reciprocal coordinates, so to speak, given by this expression. The ratio of the arc distance to delta x, the ratio of this distance to our delta x, is 1 plus f prime of x squared, very similar to what we see here. That can be expressed in terms of the normal vector. Due to the fact that the triangle we show here, where the normal vector is projected onto the direction perpendicular to our axis, is similar to the triangle here, in which we have the arc distance and the delta x. And the corresponding proportionality is easily written down, and by close analogy with this approximation, we've asserted that the surface area above an area increment dA in a plane is in the proportion magnitude of n to projection onto the k direction of n for a surface corresponding to a function f of xy lying above and or below that plane. We can add one more bit of notation, and we're going to call the surface area lying above the area increment dA. I wrote delta S because I wasn't really thinking, but we're going to call that ds. So again, if ds is a region lying above an interval dA in the plane, then if we have a normal vector to the surface at that point, we have this ratio, we multiply this number by the dA, and we get our surface area increment ds. We model that ratio, or we demonstrate that ratio with a pair of dominoes at some angle gamma, where the area of this domino projected down onto the plane is just the area we show here, whereas the area of the domino is this. This area is greater than this area, and the trigonometry of that is such that the ratio is just the secant of gamma. This area up here is the secant of gamma multiplied by this area, where gamma is the angle between the two planes, alternatively the angle between the normals to the two planes. This plane has a normal this way, this plane has a normal this way. The angle between the normals is equivalent to this angle, and we can mimic an area on any plane by aligning the lower domino with the direction of the gradient, viewing from this angle, which will give us a view of our angle gamma between the two planes. The ratio of a surface area, or the ratio of an area down here in the plane to the area of the region lying directly above that plane, being determined by the angle gamma as viewed from a direction perpendicular to the gradient. If we represent the situation by a delta y by delta x rectangle in the xy plane, then the region on the surface lying directly above this region is approximately a rectangle defined by the vectors delta yj plus fy delta yk. In other words, delta y in this direction, fy delta y in this direction, and xi plus fx delta xk. That is delta x in this direction, fx delta x in this direction gives us this vector. The region of the surface above, the part of the surface above this delta x delta y, then has an area delta A. The region above the surface, the region of the surface above our delta x by delta y increment, which has area delta A, is an approximate parallelogram, not a rectangle, as was for a moment incorrectly asserted. And the area of that parallelogram is just the magnitude of the cross product of these two vectors. That area is easily calculated. We just take the cross product of the two vectors, the magnitude of the cross product of the two vectors, and we get this expression, which is very similar to the arc length ratio that we obtained in first year calculus for functions of a single variable, where we had just the 1 plus fx squared times our delta x. Now we have 1 plus fx squared plus fy squared times delta y delta x. It follows that the area delta S in a surface corresponding to an area delta A in the xy plane is just equal to this ratio multiplied by that area increment, where we note that fx and xy are evaluated at a point in the plane region, which allows us to make sense of the expression we get when we try to build our integral by partitioning a larger plane region. We still need to reconcile our original assertion, the original assertion being that the ratio of the surface area to the area in the xy plane is a secant of gamma, reciprocal of the cosine of gamma, and calculated by the magnitude of n divided by n dot k, and that should be the magnitude of n dot k. This is not difficult to reconcile. Let's get this expression here and this expression here, so we see we're again relating this expression to this expression, this ratio to this ratio. As we've seen at least a couple of times in the past, a normal vector to our surface region can be obtained by taking the cross product of any two vectors tangent to the plane, any two non-parallel vectors tangent to the plane, and the vectors I plus fxk and j plus fxk in this direction and this direction are tangent to the plane. Their cross product is this, easily calculated either by applying the distributive law or by using the determinant form of the cross product. In general, if we project our vector n onto our vector k, the geometry will give us a triangle, a right triangle, and the angle between the n and the k vector is the angle that we're calling gamma. Bringing the triangle around so that we can view it from a perpendicular perspective, we see that the hypotenuse of the triangle has magnitude n. The adjacent side, the side adjacent to the angle gamma, has magnitude, has length equal to the magnitude of n dot k, so that the cosine of gamma, being the adjacent over the hypotenuse, the adjacent side over the hypotenuse, is indeed the magnitude of n dot k divided by the magnitude of n, and that's going to imply that the secant is the reciprocal of that, so we're going to turn this upside down, giving us this expression. And then finally, using this particular normal vector, we calculate the magnitude of n over the magnitude of n dot k. For this particular normal vector, the k component is 1, so the magnitude of n dot k is just 1. We end up with the secant of gamma just equal to this particular normal vector, but we could have used any multiple of this normal vector, in which case whatever that multiple is would have occurred in the numerator and denominator and divided out in any case, so that the secant of gamma for this particular normal vector is the magnitude of n, which is very easily seen to be the square root of 1 plus fx squared plus fy squared. And I'll quickly note an error that I made because it might be instructive, and this is on one of the clips. I decided to leave it in. In the process of defining this rectangle up here, or what I assume to be a rectangle, I found the magnitude of this vector and the magnitude of this vector, the vector j plus fyk, and the magnitude of I plus fxk. I even asserted that this does give us a rectangular region above the delta A region in the xy plane, and proceeded to find the length of this vector as viewed from perpendicular to this plane. At which point I realized that I wasn't going to get what I thought I was going to get, and realized that there must be an error, but I couldn't reconcile it at that point. So, having acknowledged that this wasn't going to work out, I went ahead and completed the calculation. I got an area equal to square root of 1 plus fy squared plus fx squared, which is fine as far as it goes, but then I got an fx squared fy squared in the product, and as I realized a little bit earlier before I calculated the delta x side, that wasn't going to work out right. And the error in my assumption was that this is a rectangular region, and it certainly isn't. At least not in general, and actually kind of never. Okay, because the k direction, the argument, the reason I asserted this is rectangular is because this vector is in a plane parallel to the yz plane, this vector is in a plane parallel to the xz plane, and I asserted without thinking that a vector in this plane and a vector in a perpendicular plane have to be perpendicular. And that can be reduced to absurdity because we can have a vector in each plane that's as close as we like to the k direction. So that this vector could be close to the k direction, this vector close to the k direction, and those vectors certainly would not be perpendicular. I decided not to make you watch me write this statement. The assertion that the region is a rectangle, that this region is a rectangle, reduces to absurdity, leading me to another statement that you want to maintain skepticism. You want to check everything. Don't believe anything, even if it kind of seems right. And keep your sense of humor. Because at some point in the study of mathematics, you're certainly going to need it.